This video covers the last section, section 2.5 of chapter 2. And it's all about the special properties water has for making life possible on Earth. And one of those reasons why it's important in living systems is that all organisms are made mostly of water, and they live in an environment dominated by water. Water molecules are polar, with oxygen regions having a partial negative charge, delta negative, and the hydrogen region a slight positive charge, delta positive. Two water molecules are held together by a hydrogen bond, so water can bond to itself by hydrogen bonds. And this gives unique properties to water that emerge in large part from this hydrogen bonding. And it gives water a higher level of structural order. And these emergent properties, due to hydrogen bonding, include cohesive behavior, moderation of temperature, expansion upon freezing, and versatility as a solvent. So cohesion plays a role in transporting water through large plants like trees. And it relies on the linkage of water molecules by multiple bonds. So you can see in this picture all the water molecules are linked, and they're linked from the leaves all the way down to the root. They're linked together, and this is all connected by water conducting cells. In the water conducting cells, the molecules stay close together because of this cohesive force due to hydrogen bonding. And it contributes to how plants can transport water against gravity. So as water evaporates up here in the leaves, hydrogen bonds cause water to leaving the veins of the leaves to pull on molecules further down the tree through this water conducting system. And this pulls up water from the roots through the rest of the tree. And that's because of this connectivity between water molecules. Another component that helps this is water can attach to the sides of the cells. So there's polar groups that can hydrogen bond with water on the side of these cells, and that helps to give water a grip to help it climb up against gravity. Surface tension is the next topic. And surface tension is a measure of how hard it is to break the surface of a liquid. It's related to cohesion, and it's due to hydrogen bonds. Hydrogen bonds give water a unusually high surface tension, and it's like on the surface of water is some kind of invisible thin film coating. And many species of insects and other animals can use this surface tension of water to walk across the water, like the case of this raft spider. Water is a great modulator of temperature. In fact, water absorbs heat from warmer air and releases stored heat to cooler air. And the hydrogen bonds that store this energy. And water can do this process of absorbing or releasing heat with only a slight change in its own temperature. So just to review some terms, kinetic energy is the energy of motion. Temperature is a measure of average kinetic energy of molecules. Thermal energy is a measure of the total amount of kinetic energy due to molecular motion. Thermal energy is transferred from one body of matter to another and is termed heat. Some ways to measure these things. A Celsius scale will measure temperature, and the calories amount of heat required to raise the temperature of 1 gram of water by 1 degree C. The specific heat of a substance is the amount of heat that must be absorbed or lost by 1 gram of that substance to change its temperature by 1 degree C. The specific heat of water is 1 calorie per grams per degree centigrade. And this is a very high specific heat. And this high specific heat is all traced to hydrogen bonding. Heat, when it's absorbed when hydrogen bonds break. And heat comes in, it breaks hydrogen bonds. When hydrogen bonds form, heat is released. And this is important for keeping temperature fluctuations within limits to prevent life. And we give an example of this of Southern California. This would be a temperature range on an August day, so a hot summertime. By absorbing and releasing heat, oceans moderate coastal climates. And you can see the relatively cool ocean reduces coastal air temperatures by absorbing heat. So you get a gradient of heat as you move farther away from the coast. Coastal temperatures are in the 70s. As you move inward, it increases. You move further inward to the deserts, and you're into the hundreds, which is about 50 miles, 60 miles inward. So water can evaporate when it changes from liquid to gas. The heat of vaporization is the heat that a liquid must absorb for 1 gram of water to be converted to gas. As a liquid evaporates, the remaining surface cools. This is called evaporative cooling. And this helps stabilize temperatures in organisms and bodies of water. So ice floats on ice or solid phase of water floats on liquid water. And a lot of this has to do with the hydrogen bonding structure of water. So in ice, each molecule is hydrogen bonded to 4 neighbors in a 3-dimensional, highly ordered structure, which results in less densely packed molecules, water molecules, than in comparison to liquid water. So as you can see, there's many less molecules in this field or volume versus the same volume of liquid water. There's many more molecules packed in. So ice is less dense. If it's mixed with water, it floats on top of the water. And in habitats, cold habitats, this is important. The floating ice, as you can see here, this is in the ocean near Antarctica. You have the floating ice, but then just beneath it, this shrimp or krill can survive in the liquid ice. And the floating ice protects the liquid water from becoming colder and turning more of it into ice. It acts as a barrier to the colder air above. So water is a universal solvent, and it's the solvent of life. And because of its polarity, water is a very versatile solvent. It can form hydrogen bonds. With ions, it actually forms shells of hydration around ions. So salt dissolves easily in water, and here's what happens. At the surface of each grain of salt, the sodium and chloride ions are exposed to water. In the oxygen regions of water molecules, they're negatively charged, and they're attracted to sodium cations, as you see here. Then the hydration shell around chloride ions is such that the positively charged hydrogen parts of water are attracted to the negative charge of the chloride ion. And this separates the ions away from the solid crystal. And they remain separated. The water forms a barrier for reformation of ionic bonds between sodium and chlorine. And water will completely dissolve because the water works on the surface and it works its way inward into the crystal until the crystal is totally dissolved. And this is just example sodium chloride, but there are other ionic compounds that dissolve easily in water by a similar mechanism. So water can also dissolve non-ionic polar molecules. Human lysozyme is a water-soluble protein found in tears and saliva, and it has an antibacterial action. This model shows the purple lysosome molecule in the aqueous environment. You can see all these water molecules, the red and white molecules associated with the lysosome. And if you look closely, water will hydrogen bond to negative and positively charged polar regions of the lysozyme molecule. So water hydrophobic and hydrophilic substances. Hydrophilic substances are ones that have affinity for water. So these are ionic compounds. They dissolve in water. Polar compounds, non-ionic, like alcohols, are also hydrophilic. Hydrophobic substances do not dissolve in water. They don't have an affinity for water. Your most common form of this is your non-polar oil molecules. And colloids are not solutions. These are going to be suspensions of particles in the water. So most biochemical reactions occur in water, and chemical reactions depend on these collisions of the molecules, in all which is affected by the concentration of solutes. The more concentrated, the more collisions will occur, the more reactions will occur. So, molecular mass, that's the sum of all masses of all atoms in a molecule. Numbers of molecules are usually measured in moles, where 1 mole equals 6.02 times 10 to the 23 molecules, or Avogadro's number. And molarity is the number of moles of solute per liter of solution. So acids and bases. Sometimes a hydrogen ion is transferred from one water molecule to another, leaving behind a hydroxide ion. The proton binds to the other water molecule, forming the H3O hydronium ion, plus charge, and leaving a hydroxide ion, negative charge. Water dissociation can spontaneously happen, but it's rare and reversible. there's certain solutes, acids and bases that disrupt this balance, and acids will increase the hydrogen ion or hydronium ion concentration in water, while bases reduce that concentration. An acid is any substance that increases hydrogen ion concentration of a solution, and a base is any substance that reduces the hydrogen ion concentration of a solution. Strong acids like hydrochloric acid dissociate completely in water, meaning they break up into their hydrogen ion and their chloride ion completely. Sodium hydroxide is a strong base, and it dissociates into its sodium ion and its hydroxide ion. And the hydroxide ions immediately combine with hydrogen ions to form water, so the base reduces the number of hydrogen ions by forming water. They come together and form water. Ammonia is a weak base, meaning that when it tracks hydrogen ions from solution and forms the ammonium ion, it doesn't completely dissociate, making it a weak base. Carbonic acid is a weak acid. It can act as an acid, but it never completely dissociates into its ion components. There's always some of the non-dissociated form around. So in any aqueous solution, no matter what else is added to it, the product of hydrogen ions and hydroxide ions is constant, and it's equal. The concentration of hydrogen ions and hydroxide ions at 25 degrees C is equal to 10 to the minus 14 molar. The pH of the solution is defined by the negative logarithm of the hydrogen ion concentration. It's written as such. In a neutral solution, aqueous solution, you got equal amounts of hydrogen ion and hydroxide ion, and they're both equal to 10 to the minus 7. So the pH of the solution would be the negative log of its concentration. So it would be the negative of negative 7, which would be a pH of 7. And acidic solutions have pH values less than 7. Basic solutions are greater than 7. Most biological fluids stay in a range of 6 to 8. And this chart gives you an idea of where different common solutions lie in the pH range. So in most living systems, you got to maintain a pH of close to pH 7 in the internal environment. And buffers are substances that minimize changes in concentrations of hydrogen and hydroxide ions in a solution. And most buffers consist of an acid-base pair that reversibly combines with hydrogen ion. Carbonic acid is one example of this. When you get a rise in pH, it responds by releasing hydrogen ions to lower the pH. So that's the reaction in this direction. If the pH drops and you get increased, which means you get increased hydrogen ion concentrations, it tends to drive it back to the undissociated form to lower the hydrogen ion concentration. So fossil fuels create a lot of CO2 in the atmosphere, and we're starting to see problems in the ocean where higher levels of carbon dioxide combine with carbonate ions to form bicarbonate ions. And this is detrimental to organisms that use carbonate ions to form their shells and coral reefs and such. And that concludes section 2.5 of chapter 2, sorry.